There we go. All right, we've already covered this. That was the last slide we had that worked. And that was back on a couple pages before. So let's see. This is the one we need to talk about now. And I just remembered something I forgot, so hold on just a second. And let me get this initiated. Whew. So hot. And you think leaving the door open would be helpful?
Yeah.
Okay. Huh? No, I think it's open, isn't it? Yeah. Okay, well, I wasn't sure if that was making it hotter or colder. Okay. Actually, I don't want to do that. I want to do this. Okay. This takes a while to go back and forth between slides, but I think it's worth it. All right, we were going to start on properties of liquid today. Any questions on anything up till now? Just to let you know how we're doing. Test 1 is still 2 people haven't turned it in, and those people I have not seen very much lately at all. They're still on the roll. They, as far as I know, have paid. I do not know why they are not in class. Okay, wait. Actually, there's 3 that I haven't received, but 2 of them I have seen very seldom, recently. Okay, test 2, I've gotten 3 in so far. I think a couple more came in today, so we'll be okay there. We're very close to having test 3, which I have ready for you. If we get far enough along today, I'll be handing it to you. All right, now this is a bridge that was actually constructed in England 1779. That was about 3 years after our country started, okay? That was a pretty long time ago. It's called the cast iron bridge, which is a little unusual because the cast iron is fairly brittle and you wouldn't have thought it would last this long, and then it rusts, and this doesn't seem to be in bad shape of rusting. Coalbrookdale, England, and it just is another showing of a bridge, compressional forces, that type of thing. And this is what you see in that. This is the other part of that figure. I've got a sneeze, sorry. Poor people at home didn't know to duck. Okay. That's the cast iron bridge. Now they're talking about what they call pre-stressed concrete. Requires tension in the cables while the concrete dries. After it dries, then the tension is released, placing the concrete in compression. And that's what they mean by pre-stressed concrete. It's an intentional thing to make the concrete tighter, stronger, and that type of thing. So you pull, you stress these. Doesn't make a lot of difference because your metal doesn't stress that much. But you stretch them, then pour the concrete. Once it's dried, then release the pressure, and then the tensile force is released and pulls the concrete back together. So the whole thing should be tighter and stronger than before. Okay. That's the first slide we'll get to in today's lecture, lesson or whatever, but that's a couple pages off. So let's go back to, sorry about having to go back and forth, but that's the only way to make this work. And we'll go from current slide here. Okay. So no questions? So we talked about the properties of solids. Today, properties of liquids. Hopefully get to gases, and then we'll be just about ready for the test. All right, the properties of liquid. We talked about before 2 kinds of forces between molecules, atoms, whatever. These are cohesion and adhesion. Does anyone remember the difference? Co meaning with or like, so that's the attraction of a molecule with another similar molecule. Like water coheres to water like crazy. They really stick together. That's why it's a liquid. It should be a gas, but it's a liquid. With that light of atomic or molecular mass. Mercury coheres incredibly tightly. It doesn't like to get onto anything else, except maybe other metals. So that's cohesion, the force of attraction between like molecules. Okay? A liquid like molasses really sticks together. Literally, it sticks together. Now, adhesion, on the other hand, think of adhesive tape. Adhesive tape sticks one material to another material. So that's dissimilar materials. Force of attraction between unlike molecules, which causes molasses also to stick to your finger. That's interesting the way they put that. In the case of water, its adhesive forces are greater than the cohesive forces. That's sort of amazing because it's very strong cohesive forces as well. Says put a glass in water, pull it out. Some of the water remains on the glass, of course. Okay? You've seen that many a time. That's why you have to dry your dishes, right? Or let them drip air dry. Okay. Mercury, on the other hand, stick most other materials in mercury, pull it out, doesn't stick at all. Mercury doesn't like to cohere to anything else. Adhere. Mercury's cohesive forces are greater than adhesive forces. They say when glass is submerged in mercury, pulled out, virtually no mercury remains on the glass. Now, I said most materials. A lot of metals, because mercury is also a metal, it'll stick all over a metal, okay? I can remember, and this is not a very safe thing to do, I didn't do it, but some of the kids at school, somewhere we're getting mercury, bring it to school, and watch it beat up and play with it, and stuff. Why is that not a good thing to do? Mercury is a toxic metal, okay, a heavy metal which can cause some cancerous type effect, not in small quantities perhaps, but it certainly is not a thing to play with. But I can remember them taking a penny and dipping it in the mercury, and it came out silver, because mercury is silver, and it looked like a dime then. And then they were thinking, we can get away and make 9 cents on this, Of course, kids in school, that was not a big deal. Okay. Kayla? Okay. All right. So, cohesion, adhesion of liquids. Now, kind of connected in some ways to the cohesion of a liquid will lead to what they call the surface tension. Now, I mentioned this with water earlier. Which do you think is denser, metal or water? What do you think? Metal, for sure. Okay? Yet, if you take something fairly light, like a needle, and drop it very carefully onto the surface of water, it floats. The reason for that is the surface tension of the water is holding so tight it keeps it from sinking. And your picture in the book there on figure 1220 shows that. Now, if you put just a little bit of soap, like drop a drop of Dawn or something into the water, immediately it sinks, because what this you may find surprising is soap really a cleansing agent? In itself, no. What soap does is break down the surface tension of water. You put water on your hands, and water is going to stick to itself. It sticks to your hands some, but it doesn't do as good a job. You put soap, and now it wets much better. And then it'll surround dirt particles or other things and get them off of it. Okay? That's what soap does. It's a surfactant, which reduces the surface tension of water. In that sense, it does clean, but it doesn't do any cleaning itself. It just reduces the surface tension of the water. Figure 1221 in your book shows, it says a mercury drop on a surface. When I've seen them, they've been more spherical, hardly any flattening out on the bottom. Now, they do show here both a liquid drop in space and a falling raindrop. And a raindrop is teardrop shaped, a little bigger at the bottom and getting narrower at the top because of the force of air resistance and, you know, a little bit of gravity too. But the out in space, where you have almost no gravity and certainly no air resistance, or, you know, not very much, they'll form perfect little spheres because water tries to reduce the surface area as much as possible, but with a raindrop it can't. Now, another aspect. So we've talked about, let me get my pen set up, cohesion. That's the force between like molecules. Adhesion, the forces between unlike molecules. Surface tension, which frankly to me, is it S or SS, not T? Surface tension, which is related to cohesion of the water molecules, and that makes it very hard to penetrate the surface. Now, I think I mentioned to you before, people diving off really high dives into water, if you're not careful, you can break fingers, jam fingers, break a neck, dislocate shoulders if you go in wrong, because the surface tension of water is so great. If any of you have jumped into a pool of water and done what they call a belly flop, you know how hard that surface tension holds together. It's not a pleasant experience, okay? So those are just various aspects of surface tension. And I think the other one I mentioned, I'm sort of tempted to do it with one of Jalen's water bottles, but I don't think we really have time for it. You can fill, say, that little cup that he had there, you can put water in it and keep putting water, and actually you can put enough water till you see water over the top of the cup before it ever starts spilling, because those water molecules are hanging onto each other like crazy. That's surface tension. Okay. The next topic mentioned here is viscosity. Anyone know what viscosity means? What does it mean for a liquid to be viscous?
It says the internal friction of the fluid caused by molecule attraction.
Okay. Yeah, so again, I tie this in with cohesion. The internal friction of a fluid caused by molecular attraction, which makes it resist the tendency to flow. If you've ever poured, water doesn't have that great of viscosity. It's pretty low. Alcohol is very low. Not that I poured that much alcohol. But think of, there's Tiffany. Good deal, thank you. Found you, there you are. Okay. Okay. I was thinking of honey. Their example of molasses would be just as good. As you tend to pour that, it comes up, just hardly moving at all. High viscosity, okay? I don't know, y'all are probably way too young to remember the old Prel commercial. Does anyone remember that? Drop a pearl into Prel and it takes so long for it to go to the bottom. That's how luxurious Prel, it was a shampoo, was. Long time ago, that was the thing. High viscosity. Things that affect viscosity is, of course, the type of material, but the other thing would be temperature. Usually, the higher the temperature, the further the molecules move apart, so it's easy for them to move past each other. And I think you can imagine that if you have some honey or sorghum or molasses or something, especially it's been in the fridge and will hardly pour at all, put it into the microwave for just a few seconds, and there it pours much, much more easily. Heating it up decreases the viscosity. Now, that leads to another issue. In places that have extreme changes in temperature between summer and winter, I'm thinking places perhaps like Minnesota, Wisconsin, and places like that, get incredibly cold in the wintertime and yet still get pretty warm in the summertime. Okay? Quite often people there have to change their oil, or when they change their oil, they adjust it for the temperature of the year they've got. Because if you use the same oil in the wintertime that you did in the summertime, it may be too viscous to really lubricate well. But if you use the same oil in the summertime you used in the wintertime, it may be too liquid. It doesn't, the parts will rub together. So you have to be very, very careful. Now, a lot of people will confuse viscosity with density. Seems like a more dense material would be more viscous. Not necessarily. Oil is more viscous than water, especially at regular temperatures, and yet it's much lighter density. Oil always floats on water. So don't confuse those two. Now, the next topic is capillary action, and we talked about this last time. Now, I can't figure out why I was talking about it if we hadn't gotten to it in the book. But what is capillary action? And it actually works one of two ways, depending on your material. If the material is higher cohesion than adhesion, or higher adhesion than cohesion. Remember when we mentioned that? I said some of you, if you've ever stuck a finger for blood and taken a sample from it, you get those little capillary tubes. You just place it near the drop of blood, sucks it right up. That's capillary action. The tube is really tiny, so the blood adheres more to the glass than it does to itself, coheres to itself. So it just sucks right up into the tube. That's capillary action. Sometimes getting it out of the tube would be more difficult too, because it's stuck in there. I give the example sometimes. Have you ever been to a fast food place or some type of place that serves hot coffee, and what they serve it to you with is coffee in a cup and one of those little bitty swizzle sticks that's hollow? And you can drink your coffee through that thing, but you get very little coffee, and that way it cools off faster or more, and you won't get a mouthful of it and burn your mouth. You'll just get a little bit and burn a little bit in your mouth, right? Now, can you imagine taking that little swizzle stick that you use for hot coffee and trying to drink a milkshake through it? you will pop your eardrums trying to suck the milkshake up that tiny little capillary tube. And the reason is the material, well, milkshake is far more viscous, bigger chunks of things in it, so it's harder to get through, but then too it sticks to the side. The hot coffee, some of it sticks to the side, but generally not as much. Okay. Now, I think that's leading to just about the next slide. If you got your books, you can see figure 1223 has really nothing to do with viscosity or capillary motion. It's just with the fact that liquids seek their own level and maintain that level. Except unless you do have capillary tubes. And figure 224 shows what 225 is also showing. So let me get out of this. And get to this one. Okay. Now, this goes capillary action and let me get the current slide. Okay. Here's water, and here's 3 glass tubes. I assume they're glass, whatever they happen to be. Similar tubes. One with a big diameter, one with a, and when I say big, if they're capillary tubes, they're pretty small. But one has a small diameter, one has a much smaller diameter, one has a tiny diameter. Okay? Well, here's what's happening. And you can almost see it and imagine what's going on. You put this in the thing and notice what's happening. Okay? Sort of hard to. Let me see if I can do it with this. Can you see the thing? Okay. Notice there the water already is crawling a little bit up the side of the pan. You see that? And that's because the adhesion of water to the container, water likes to adhere to that, so it actually crawls up, and then it pulls other water molecules by cohesion up with it. Okay? Well, put a capillary tube there with a fairly small diameter, and you see on the outside that's pulling the water up, okay? But also on the inside it is. And since the inside, the walls are close together, and it goes around in a circle, where the water moves up the capillary tube, it pulls more and more water up there, okay? So it will rise far more than it will in the pan. Well, same thing here. With a smaller tube, it goes even higher. And with a tiny tube, it really, now this is exaggerated pretty big time, I think. But that's what's happening with water. And the reason is water, and you'll see it here, is crawling, pulled up the glass tube. Okay? Blood does the same thing because blood is mostly water. Now, here's something you have to sort of be careful for. When you're making measurements, let's say this was a graduated tube or something, you have to be careful where you're measuring that because the water is high on the edges but dropped in the middle. So what are you going to measure from? Okay? Quite often they'll say measure at the bottom of the meniscus. And that's what you call this curved shape is the meniscus. So you usually measure at the bottom of the meniscus. Because very little water is up on the sides. It might look like it is looking through it, but in reality, that's just a very thin film. So measure to the bottom of the meniscus. Okay? Unfortunately, mercury does the opposite. Mercury does not adhere to the glass at all. Okay? Water does some, and water also coheres, but mercury only coheres to itself. So you put it in a thing, and notice it tries to avoid the side of the thing as much as possible. It bunches up in the middle like, stay away from me, glass, you know. It doesn't like it all. So you put 3 similar tubes in a pool of mercury, and actually the capillary effect goes in the opposite direction. Because the it repels the side of the thing. Notice it repels a little bit the side of the container, a little bit the side of the outside of the glass, but on the inside of the glass, where it's closer together, it's really pushing down. And it's trying to avoid that like crazy. And the smaller the tube you have, the more it pushes down, trying to avoid that contact at all. Okay? That's capillary effect in a adhesive material like water and a cohesive material like mercury. Now, of course, water coheres too, but it has greater adhesion to the glass or to the tube than the mercury does. All right. Here's kind of a summary of that. I don't know. Most of you have books now, don't you? Okay. It's on page 328. Experimentally, and right above there you'll see the meniscus. And again, if you're measuring mercury, you do from the top of the meniscus. Here you do from the bottom with water. You go with either the lowest point in water or the highest point in mercury. Okay? Experimentally, scientists have found that, number one, liquids rise in capillary tubes. They tend to wet, and are depressed in tubes. They tend not to wet. In other words, whether they adhere to the tubes or not. Number two, elevation or depression in the tube is inversely proportional to the diameter of the tube, because the bigger the tube, the less the elevation or depression. The smaller the tube, the greater the elevation, just like we saw here. And number three, the elevation or depression decreases as temperature increases. Same type reason before. The higher the temperature, the more the molecules move, and then the less they cohere together or adhere to the sides. Now, I was talking some about oil viscosity. You can read this little blurb about it. In areas such as where we live, where, yeah, there's a difference between summer and winter, but it's not that great. Well, a lot of times here we'll use what they call blended oil. And by the way, if you ever put oil in your car or lawnmower or other things, what oil is sold by and measured by is by SAE numbers. Those indicate viscosity. SAE 30 is a lower viscosity than SAE 45, okay? 60 or 90, okay? The higher the number, the more viscous it is. Well, and say those far north areas have extreme differences in temperatures, summer to winter. You'll use a low viscosity oil in the wintertime and a higher viscosity oil in the summertime. Here, what we do is use what they call a blended oil, and that's usually something like 20-50 or something like that. It sort of runs a range between the two. So it's not just SAE 30, but 20-50. Okay. Let you read this. 10W40. I'm sorry, there it is. 10W40. 30 is a common one. 10W40 is also 5W20. You can read that and see, and that basically tells you the temperature at which it'll still be working the way you wanted it to. All right, that I think pretty much wraps it up for liquids. And if you thought that was fairly short, look at 12.4. That's properties of gases, even shorter. So let me get out of there and just mention a few things with gases. Okay? Okay. Wrong button. Now, do you remember back at the very beginning we talked about the phases of matter? Some people call it states of matter. Solids keep their own shape. They keep their own the volume. Everything stays fixed. That's because the molecules are fixed in that crystalline structure. Liquids, on the other hand, the molecules are broken from the crystalline structure and they move past each other easily, but they don't get out too far away from each other. So they keep the adhesion of the proximity, but they don't keep the fixed position. So they keep their own volume, but take the shape of the container. But then gases, on the other hand, free fall for all. They just float anywhere they want to. They don't stick together. They fill a room. You know, if you had just a little bit of ammonia here, soon the odor will fill the whole room. It takes a while to do. So another characteristic of gases, and it's also of liquids and solids, okay, that's expansion, especially thermal expansion. So there are other things that will cause gases to expand, more so than liquids and solids. Because solids, remember, keep their own shape, okay? The only motion of their molecules is vibrational. But if you heat it up, they vibrate faster and they get a little bit further apart. So solids do expand when they heat and contract when they cool, but not by much, by just a little bit. Now, I don't know if you've ever noticed when you drive onto or off of a bridge, this always seems to be ding, 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 ding. Okay? What that is an expansion joint. Okay? If they were to have built that bridge in the coldest day of winter and butted those steel joists right against each other so you wouldn't have that bump when you go by, then the next summer when the temperature goes up, that's going to buckle. And actually, I've seen pictures of railroad track that on very hot days have literally bent and buckled and trains derailed them. The reason is the expansion joint wasn't big enough. On the other hand, I think I gave this example before. If you were stringing the wires between power poles, and you were doing that in the hottest day of summer, and you thought, well, let me conserve the length of wire that I'm using here and make them just as tight as possible. Then the next winter, when it gets really cold, it's going to break that pole, and they will. That compression of the reduction in size of the metal as it cools is enough to break a big old power pole. Okay, so solids expand and contract, heating and cooling, but to a very small extent. Liquids also expand and contract when heating and cooling. A little bit more so than solids, but not very much. Gases, big time. Now there's one major exception to that. It's about the most unusual substance on the planet, and yet it's one of the most common substances on the planet. What substance is that? I've already mentioned it a couple times. I said it really should be a gas, and it actually is a liquid. Because its molecular weight is so light, it should be a gas. But because of its surface tension, it's a liquid. What was I talking about? Belly flop in the pool. Water! Okay? Now, here's another reason water is so strange. Water is just about the only substance I know, certainly the only common substance, that when you cool water, it does indeed very slightly contract until it gets down close to freezing. And what happens? It expands like crazy. I mean, not super much, but it does expand. You know that. How do you know that? What are some examples of that? Most materials, when they cool, they shrink. But water, past like 4 degrees Celsius, so just 4 degrees above freezing, which would be about 40 degrees Fahrenheit, When it gets below that, water starts expanding. The reason is water, when it freezes, it goes into a crystal structure. And that crystal structure actually is more expansive than the surface tension of the water before was. It held really tight. When it starts freezing, the molecules have to get into the positions, and that actually swells some. Okay? How do you know that water expands right before it freezes? Does anyone still put water in trays and put it in the fridge? No one does. The refrigerators make it. Okay, hang that one up. Okay. Someone was telling me, it was a neighbor of ours up at Smith Lake. She was saying that really cold snap they had back in January just got brutally cold, January, February 1. It had been fairly nicely warm and then suddenly got really, really, really cold. Something happened in their, they have a little apartment that's on the other side of their deck. And they had just finished putting new tile on the floor, new sheetrock, new everything. It turned really, really cold. Guess what happened? And they had a bathroom in there, you know, shower, that kind of stuff. It got really, really cold, and what happened? Why did the pipes burst? Because water expands when it cools below 4 degrees Celsius. Unbelievable. Water is strong enough to break metal pipes. I bet you, I mean, we've had it happen in our house. I bet you, most of you, if you haven't, you probably know someone who has. Water will break metal, okay? It expands that much. So, that's the only, now, that sounds like a pretty bad thing. Are you mad that water expands when it freezes? Is that a bad thing, a good thing, or indifferent? Trick question, huh? Could you tell me what's in your cup there? Is that okay? Did you have any liquid in it before? What was it? Tea or coffee? It's what? Yeah, but was it water? Okay. Well, but it has ice in it. And is all you had in ice, or did you have a liquid in there before, earlier? Okay, and what happened when you had the liquid in there? Where did the ice go? It floated. It went up. And why is that? Because ice expands, water expands when it freezes. Okay? So that's sort of nice. That way, you know, the hot liquid would go up and the cold liquid down. But when ice is up there, then all of it gets cold. So that's sort of a good thing, isn't it? Actually, it's better than that. Let's go back to Minnesota and these places where when it gets bitterly cold in the wintertime, I mean absolutely frigid in the wintertime, guess what? Their lakes and other bodies of water completely freeze over. Okay? That doesn't happen much here, ever. But up there it does, frequently. They drive vehicles out on the lakes because the ice is that thick. And they do ice fishing. It's kind of crazy. Okay? If water froze from the bottom up rather than the top down, everything in that lake would die. The fish would die, the insects would die, just about everything would. But fortunately, when water freezes, it rises, and that leaves usually an air pocket and some liquid water still in the bottom. So those things can still live. If it was the other way around, everything would die. And guess what? Ecosystems would not work then. Thank you, water, for being strange. All right. So that's one thing. Gases, even more so than liquids. They expand like crazy when they heat. Okay? They also expand like crazy when you release pressure from them. If you have something at a very high pressure, it will get smaller. At a lower pressure, it expands with the same number of molecules, same temperature. So that's expansion. A property of gases, which is the rapid random movement of molecules, causes the gas to completely occupy. So that's, let me get my pen back. Every time I change slides, well, I can't get my pen back. There we go. Okay. Expansion. Gases expand very quickly when you heat them or when you reduce the pressure. Okay? Now, very little do solids do this, but a little bit. More so liquids do, but not nearly as much as gas, and this is diffusion. Does anyone know what diffusion is?
When the molecule of a gas mixed with the molecule of a solid, a liquid or another gas.
Okay. I use the example of ammonia, but it works for gasoline. Can you tell when you left the cap off your gasoline can that you're doing the lawnmower? Very short time, you're going to smell the gas, right? Same type thing. That is gas diffusing. Let me give you a little bit more technical definition. Diffusion is the movement of a material because of a concentration gradient. The greater the concentration, the more the movement, the concentration difference. So you have lots of gas molecules in that bottle of ammonia, thing of perfume, gasoline can. You open it, now little gas molecules, very few gas molecules or ammonia molecules out here, so they diffuse. They go from areas of high concentration to low concentration. Now this is not a gas, but it's the illustration I use for it because I usually like messing in the garden. We don't do much at our current house because it's so shady. But I would use the example Bermuda grass. Bermuda grass will move from the concentration, high concentration in your yard, right into your flower beds or your garden and stuff, it trying to get to that area of low concentration. Think of Bermuda grass, that's diffusion. Going from an area of high concentration to low concentration. Okay. Now, here's another concept, and it relates to both liquids and gases, because it includes both. When you say the word fluid, you usually think which one? You usually think liquid. Gas is just as much a fluid as a liquid is. So when you talk about fluid dynamics, fluid anything, the properties of fluids, gases and liquids are both included. And that's all, folks, for 12.4. Okay? Now, bless you. 12.5. I told you, if you thought 12.3 was short, 12.4 is 4 short paragraphs. Very short paragraphs. 12.5, I think I'll go to a new slide here. 12.5, the topic of it is density. Does anyone know what that term density means? And we actually have two terms. Anyone know what it means? Definition of density? Two kinds. This book uses dm is a mass density, okay? Okay? Whereas mass, the reason they say mass is that is the numerator. It's an object's mass divided by its volume. Remember, capital V is usually volume. So it's an object's mass divided by its volume. Little v is usually velocity, so don't confuse those. Whereas the other kind, and this is the one we use mostly in the U.S. customary system, SI system, they almost always use mass density. U.S. customary, though, we use weight density, D sub W. Now, not all texts use these same symbols, but this one uses capital D. And what a weight density is the weight. Now, I usually use little w for weight, but this book uses F sub w. That's the force due to weight, gravitational attraction, divided by volume. Okay? Now, are masses and weights equivalent? Generally, if the mass goes up, its weight goes up. If the weight goes down, the mass goes down. Yeah, they react similarly, but remember, mass is an invariant. Okay? Weight does vary based on where you are in the gravitational field. And since we spend our entire lives on the surface of the earth, or very close to it, our weight doesn't vary unless we eat more or eat less. You know, that's the only thing that varies it. So, in many respects, you can use either one of these. Unless you're going into outer space or something like that, then your weight can change, but not your mass. So, most of the time, it really doesn't matter. Okay? The mass density is usually given in these units, kilograms per meter cubed. And frankly, that is usually a very large number. And here's why. Kilogram is a fairly reasonable thing. I'd say this book probably has a mass pretty close to a kilogram, maybe a little less. It's pretty hefty, okay? But what's a cubic meter? Okay, I'll open it back up. I'm going to close the door just temporarily here. Okay. Now, that knob is pretty close to 1 meter above the floor. And that width is pretty close to a meter. So if I stood that far from it, that would be 1, 2, we don't quite even, about here, about that distance from it. Now if I had a huge cube that was that wide, that tall, and this deep, and say filled it with water, anyone have an idea about how much that water would weigh? Pretty close to a ton. Because water has a mass density of 1 gram per cubic centimeter, which turns out being 1 kilogram per liter. So when you go and buy a liter Coke in the store, I don't know if they still sell those. I know they do 2 liter and 3 liters. But 1 liter of something in the store, a little more than a quart, that's usually about a kilogram. This would be 1 meter by 1 meter by 1 meter. Okay, that's 1 cubic meter, and that would be 1. If it's a gram per cubic centimeter is the density of water, mass density of water. 1 gram per cubic centimeter. It takes 1,000,000 cubic centimeters to make a cubic meter. Okay, because you got 100 centimeters this way, 100 centimeters that way, 100 centimeters that way to make a meter, meter by meter and meter. That's 1,000,000 cubic centimeters. 1,000,000 grams would be 1,000 kilograms, and 1,000 kilograms is 1 metric ton. That's a lot of mass. So when they do use this unit, your numbers are usually very big. So quite often they don't use it. They use grams per cubic centimeters, and that makes a nice round number, useful number. Okay? So the mass density of water, like I just said, water is 1,000. And why do they put a bar over this. It's not. It's exactly 1,000. It doesn't need a bar over anything, but they put it there. Kilogram per cubic meter. Okay? That's because they like using 3 significant digits. Okay? Now, the weight density of water, and weight density in the U.S. customary would be pounds per cubic foot. Okay? Now, a cubic foot is much smaller than a cubic meter. Much smaller. These tile pretty much, I think, are what they look like, about 1 foot. Pretty close. I think they're about 1 square foot tile. So if you had 1 foot by 1 foot by 1 foot, that's 1 cubic foot. That was 1 cubic meter. I mean, hugely more. Well, a pound is a little bit less than about 2.2. 1 kilogram weighs about 2.2 pounds. So therefore, you've got a smaller unit in pounds, so you have more pounds. So in water, that would be 62.4. Yeah. I was thinking salt water. 62.4 pounds per cubic foot. 2 reasons it's a smaller number. The main one is a cubic foot is so much smaller than a cubic meter, so you don't need as many pounds. Okay, so that's the weight density of water. All right, and conversion factors must often be used to obtain the desired units. That feels like there's an example coming up, doesn't it? So let me get out of this. I'm going to come right back to it, but I want to show you the next slide here. Here it is. Now, this is going to be a pretty busy slide, and you probably can't read it maybe from everywhere that you are, but these are some of the densities of various substances. Now, the kilograms per cubic meter, huge. The weight density, pounds per cubic feet, much more reasonable. Now, I'm going to tell you this. If you were dealing with grams per cubic centimeter, which is a really reasonable number, all you have to do is move your decimal to where the commas are, and that will give you that. So aluminum would be 2.7 grams per cubic centimeter, which is 2,700 kilograms per cubic meter. That's because it's such a huge volume there. The weight density of aluminum, about 169 pounds per cubic foot. Okay? In other words, if you had 1 cubic foot of aluminum, that's going to weigh about 169 pounds. Okay? Brass, much denser because it has copper in it. That would be 8,700 kilograms per cubic meter, 8.7 grams per cubic centimeter, 540 pounds per cubic foot. Concrete is sort of an average, 2,300 kilograms per cubic meter, 2.3 grams per cubic centimeter, about 140. So you see, here they go. Like I said, because brass has a lot of copper in it, it's much closer to the density of copper. Copper is more dense, quite a bit more dense than aluminum. Okay? Cork floats like crazy. Very low density. That would be 0.24 grams per cubic centimeter, 15 pounds per cubic feet. Okay? Something to keep in mind. Compare all this always with water. There it is, okay? For water, the density is 1,000 kilograms per cubic meter, which is exactly one gram per cubic centimeter. The reason it's exact, that's how we define what a gram was. Back when they started the metric system, they got the length first, a meter, and then said, that's pretty long, so let's do hundredths of a meter, centimeters. That's pretty short. That's like the distance across your little fingernail. I can handle that. And then they said, well, what if we had, and the most common material on the surface of the earth is water, so what if we had 1 cubic centimeter of water? That'd be like a little bitty sugar cube, you know? Oh, but it's water, not sugar, okay? Let's name that 1 gram. So the density of water is exactly 1 gram per cubic centimeter, which makes it exactly 1,000 kilograms per cubic meter, which you don't need the bar there because it's exact. That's an exact number, okay? And that's 62.4 pounds per cubic foot. Well, anything that's less than 1,000 here, like cork, ice, not much less, but a little bit less, wood, that's like pine wood, alcohol, gasoline, oil, anything that's less than water is going to float on water. Anything greater than water will sink in water. Okay? So cork floats like crazy, ice floats, pretty well. Iron sinks, but not as bad as copper. See, copper is denser than iron. Lead really sinks, okay? 11.3 grams per cubic centimeter, 11,300. But catch this one. Look at that liquid. Mercury, 13.6 grams per cubic centimeter, 13,600 kilograms per cubic meter, 846 pounds per cubic foot. Guess what? Lead floats in mercury. If you had a lead ball or lead anything, chunk of lead, you put it in a pool of mercury, it's going to float. Mercury is that dense. Okay? A few other things to note. Ice being less dense than water, so it floats. We talked about that. Seawater is just slightly denser than water. That was the 64.0. That was the one I was starting to put down. Now, what does that mean for us? Ever been swimming at the pool? And then sometime later go swimming in the Gulf of Mexico? Which is easier to swim? Okay. Why? Because of the waves and stuff? Okay. Ignoring the waves. It was very still at the Gulf of Mexico. Early morning, late evening when there was hardly any wind. It's easier to swim. It's easier to float in salt water. In fact, a lot of times you don't even need a raft. You just float. I'm sort of a sinker, so I tend to go down. But ships, if they're at sea in fresh water, they go lower. In salt water, they ride a little higher. And you'll see that markers on the sides of vessels that do both. They have 2 scales where the water line is. Okay? Seawater is just a little denser than fresh water because it has salt dissolved in it. Okay, when you get up here to air, you have to specify what pressure you're at. 1 atmosphere of pressure, just about what we normally are. Air is only 1.29 kilograms per cubic meter. Goodness, that's like 0.081 pounds per cubic foot. Really, really small. Ammonia, even lighter than air. Carbon dioxide, quite a bit denser than air. Carbon monoxide, unfortunately, just about the same as air. Okay? Helium, very, very light. Hydrogen's the only thing lighter than helium. Extraordinarily light. Okay? Nitrogen's a little dense. This is hard to say. It's not denser than air because it's almost, most of air is nitrogen, like 78 to 80% of it is nitrogen. So they're very close to the same density. It's the oxygen that makes air a little bit denser because oxygen is denser than nitrogen. Propane is even denser than that. Okay? Now, this is a tough situation to say. I was starting to say, if you were in a building that was burning and you're trying to make your way out, one tendency is to get near the floor level because the hot gases rise, and you're more likely to be too hot up here than you are down there. So it's much more comfortable to be traveling right on the floor because heat rises. The disadvantage of that is if it's burning, your carbon dioxide is going to be settling down there, whereas your oxygen is going to be further up. So you see, in some sense, it's not a good idea to get low. Okay. But on the other hand, how many hands do we have here? A lot of times the materials that may be burning, that may contain in their residue and in the exhaust from the burning harmful things. I'm thinking polyvinyl chlorides and things like this that may be in the room where it's being burned. Those are usually low density when they burn, and so you get down to get below them. So it's sort of a, just get out of a burning building, okay? That's the point. But be careful. Now, what I said about carbon monoxide, it's almost the same density as air, so it's going to be everywhere. You can't say, oh, we'll get low, you'll get away from it. No, it's going to be everywhere, okay? So, and it'll kill you, and you don't realize it, okay? Tough stuff. So those are just representative densities. All right. That's the last slide they're going to show in this. So, in fact, I think I'll go on and get out of the, well, no, let's keep it because we might need to come back to it. Okay. Let's go back to our other slide. And let's do example 1. Find the weight density. What symbol do we use for weight density? D sub W. Okay. Now, see, when I see D sub W, I think density of water. I just have to get away from that. That's weight density of a block of wood, and the wood is 3.00 inches by 4.00 inches by 5.00 inches. Boy, that's very precisely cut. With a weight of, and what symbol do we use for weight? F sub W. F sub W. dW is density, weight density. F sub W is the force due to weight, or in other words, the weight. The weight of 0.700 pounds. 0.700 pounds. Okay, we're looking for weight density. And what's the definition for weight density? The weight divided by volume. Okay? Now, we got to calculate the volume. We don't know it. How do we calculate volume? This is a block of wood. They show a picture of it, but we don't have that. It's in your book. Sorry. How do we calculate volume? Length times width times height. Now, I don't know which they're calling this. I would call this the length, that the width, and that the height. So you just multiply the 3 together. What would that be? I do it. 5 times 4 is 20 times 3 is, so that'd be 60 cubic inches. Okay, divided, and that's divided into 0.700 pounds. Okay, now this will give you an answer. However, most of the time we don't give densities in pounds per cubic inch. What do we usually do? What was our table? You got your book open? Right, the same page as example 1. What is your weight density usually given in? No, that's work. Weight density. Pounds per cubic foot, right? So we've got to do a conversion here. We love our conversions, don't we? Yes, we do. Okay. And we want this answer to be in pounds per cubic foot. Okay. We're given pounds per cubic inch. We're not worried about the pounds. Those are fine. But what we have to do is change the cubic inches to cubic feet. So what unit will you put where? I put 2 blanks there. The first is for numbers. Don't worry about the numbers yet. We are worried more about the units. Always put the units in their place. So which one's going to go where? Between inches and feet, one's on top, one's on bottom. Which goes where? Make a guess. Inches on top. Good guess. Okay? And that leaves feet on the bottom, which is usually where your feet are. Right? No, that's beside the point. Okay? Now, while we got it in inches and feet, how many inches are in a foot or how many feet in an inch? 12 inches is 1 foot. But we've got a problem, Houston. We're in cubic inches and cubic feet. So we got to cube the unit, but that means we also have to cube the numbers, right? Now the cubic inches will go out. They've been dating, and we got to deal with this, okay? So that would be 0.700 pounds divided by 60, okay, times 12 cubed. I don't know what 12 cubed is right off the top. I know it's 144 times 12, but someone got a calculator? Give it to me. Okay, that will be divided by 1 cubic feet, because 1 cubed is that cubic foot. Okay, and that's going to equal our weight density in pounds per cubic foot. Okay, so multiply 0.7 times 1728 divided by 60. Second? Oh. 12 times 12 times 12. Or 12 cubed. That's what she told me. I'll take her word for it. That sounds right because 144 times 12. Yeah. No. 1,728. How many cubic inches are in a cubic foot? Think of this. Picture a ruler, 12 inch, 1 foot long. Okay? That's got 12 inches. Okay? And inches, fairly short. You got 12 inches up, 12 inches this way, 12 inches that way. Okay? Multiply 12 by 12 by 12. Well, 10 by 10 by 10 would be 1,000. So this has to be well over 1,000. So multiply 0.7 times 1728 and divide by 60. And what do you get? A little louder. 20.16? Is that what you said? So I'm going to put that as 20.2. Because the 6 would round the 1 up to. Let's see what they got. Oh my goodness, they got it right. 20.2 pounds per cubic feet. Now, think back. Water, 62.4 pounds per cubic feet. That's going to float very easily. Okay? And wood usually does float. Okay. Ready for example 2? Yes, I can tell you're enthusiastic about it too, right? So, let's go to example 2. Find the mass density. What's the symbol for that? D sub m. The mass density of a ball bearing with a mass of 22.0 grams and a radius of, ball bearing means perfect little sphere, the radius is 0.875 centimeters. Okay. Now, my tendency is going to leave this in grams per cubic centimeter. I'm pretty sure the book is going around it to, or change it to kilograms per cubic meter, which I find stinks, but we'll do it. Well, let's first do grams per cubic centimeter. Well, we don't have cubic centimeter, we have grams. Or do you want to change the grams to kilograms? We can do that too. Which you want to do? It's up to you. Second? Change it to kilograms. Okay? What is that mass in kilograms? Any ideas? It's pretty easy to do. We can use our conversion factor if you want to. Anyone know what it is? Should we use the conversion factor? Okay. So this would be, the mass would be 22.0 grams times blank blank equal blank kilograms. Right? So forget what the first number is. What is your second number? I mean the unit. What unit goes where? Goodness, my eyes hurt. I'm having trouble focusing. I think what happens, that happened to me earlier today, this computer is sending up heat, and I'm sitting here doing this, and that's just drying my eyes out like crazy. Okay? Sorry. If I start watering, it's not because I'm sad. Okay, never mind.
Is it easier for us just to keep it like what it is instead of trying to convert it to kilograms?
Okay. To get the answer they have in the book, we're going to need to go there. We can go with it like it is now and then change at the end, or you can change now. It's up to you. Pay your money and take your choice. You've already paid your money, so take your choice. What's that? Well, that's the thing. A lot of physics books make it seem like the units are more important than the physics. And they give you these problems and just mess up the units like crazy. And you spend half of your time dealing with units and not dealing with the physics of it. But that's just how they do. I know when I took physics, that was the thing I liked least about it. Them doing all the unit changes. I said, look, if you wanted that units, measure in that units in the first place. Don't, whatever. You want to do the change? What will you do? Always put the units in their place. So use that second. Kilograms on top. Grams on the bottom. How many kilograms in a gram or grams in a kilogram? Which? Say again? Yes, a kilo means 1,000. So kilograms means 1,000 grams is 1 kilogram. Okay? Think of it this way. This book is about a kilogram. An aspirin tablet is about a gram. Okay? You need about 1,000 aspirin tablets to weigh as much as that book, right? Okay. So what does that do? See, your gram units cancel out now. And how do you get kilograms? Divide the 22 by 1,000. What do you get? It's real easy when you're dividing by 1,000. You move your decimal 3 places. Because you see, you're moving that decimal 3 places to make that a 1 down there. So this is 0.022. And actually, you do need that next extra 0 there because you need 3 significant digits. And the 0 in front of the decimal and before your number, those aren't significant. The one at the end is significant. So there's your mass in kilograms. Okay? Believe it or not, that was the easy part of the problem. what's the next part? You need, did you ever give me the formula? What is the formula? I think you may have said it, but what is it? Mass density? Mass over volume. So we got the mass. Fine. In kilograms. Perfect. Wonderful. But now we got to get the volume. What they gave us was the radius. Okay? Which is a bizarre thing because radii are very difficult to determine. They should have given us diameter, but that would have made it a little more difficult. So we'll live with radius. How do you get the volume out of the radius? Anyone know? Anyone know how to get volume out of radius? Here we go. Say again? I can't hear you.
Yeah, you divide 3.
Okay, yeah, okay. 4 over 3, I got you now. And what else? That's not all of it. 4/3. If you look to the back inside cover of your book, you'll see formulas from geometry. The top ones are planes, meaning area formulas. The bottom ones are solids, meaning three-dimensional. And the very bottom one down there is a sphere. That's what we're dealing with here. A ball bearing is a sphere. Okay? And what's its volume? 4 over 3 what? There's more to it. Say again? Where do you see that? Oh, no, that's a pi. Okay, I got it. Pi r cubed. Okay? So the volume here is 4/3 pi r cubed. All right? Now, again, the question, do you want to get your radius, leave it in centimeters, which is pretty small to begin with, or change it to meters, which is really, really, really small? I didn't say this earlier, but remember tonight we were going to go an extra half hour because of next Thursday. Is that right? Is that the last Thursday in the month? Okay, wow. Month's disappearing fast, isn't it? I've got to leave early. So, question is, do we leave radius in centimeters, or do we change this to meters? You want to change the grams to kilograms early. We did. You want to change the centimeters to meters early. Up to you. Got to do it at some point. So, say again? Change it now? Okay. So we're going to change this blank blank to blank meters, because that's what they measure the volume in. Cubic meters. What unit goes where? Always put the units in their place. Always put the units in their place. What unit goes where? Meters on top, centimeters on the bottom. That way your centimeters can cancel out. You see? Now, how many meters in a centimeter, or how many centimeters in a meter? Say again? How much? Do you say 10? Okay. How many cents? 100. How many cents in a dollar? 100. So it's 100 centimeters in 1 meter. Centi means 100th of. Okay. So it takes 100 centimeters to make a meter. Okay. So that means we're going to move the decimal 2 places that way. So that would be 0.00875 meters, which is a very small number. Okay? So now to get the volume, that's what we're going to use. 4/3 pi. Pi is just a number. And 0.00875 cubed. And this will be meters cubed. And if you thought 0.00875 was a small number, what happens when you cube it? It gets even smaller. Anyone got a calculator? I'm guessing it'll give it to you in scientific notation. 0.00875 cubed. Anyone got it yet?
So are we multiplying? After you got your number there, then you put it down, you multiplying that times.
Okay. Okay. The formula is 4/3 pi r cubed. Now that's the radius in centimeters. Y'all wanted to convert it to meters to begin with, so that's the radius in meters. A very tiny little number. And you plug that into your formula for your r. If you had stayed in centimeters, it would be that number, but in meters, it's that number, and then you cube it. Then multiply it by 4 times pi divided by 3. Anyone do it yet? It's an incredibly small number. Anyone got it? Anybody at all? Don't be scared if it's a very small number. It is. Please, somebody tell me. I don't have a calculator. I can do one on my computer, but it'll take a while. What you get? Huh? Oh, you do?
No, I don't.
Okay. All right. So, you want to do the whole thing or just that cubed?
I guess the cube part first.
Oh, okay. You want to do the cube part. Okay. I see what you mean that you don't know. Okay. You know, there's not one single key that does it, so you're going to have to do what it means. What does it mean to cube something? Multiply it by itself 3 times. Now I'll show you one little shortcut you can do on here. A lot of calculators have a key that you can do that. This one doesn't. It goes up to square, but it doesn't do cube. So, where did you turn that in? Okay. Here's what you do. You want to just do that first?
Yes.
Okay. So it's 0.00875. Now what I'm going to do is first square it. That's by itself. And then multiply it by itself again. 0.00875. And hit equal. Told you it was a small number, didn't I? Tiny number. 0.000000067 something another. Right? Now, I'm going to multiply that by 4. Multiply that by pi. Let's see if you have pi on your calculator. I don't see it. Okay? And since I don't see a calculator, 3.1416. Okay? And then divide this by 3, because there's your 3 there. And hit equal. And you get 0.00002806.
I'm very lost.
Huh?
I'm very lost.
How so?
I got this part,
Right.
but then when you did the
Times 4.
times 4.
Times pi, which is 3.1416.
Okay.
Time and divide it with 3.
Okay, let me see.
Yeah. Do it one step at a time. Someone read that number off to me again. See, now they left it in grams per cubic centimeter, then they converted to kilograms per cubic meter. So, but y'all want to do it this way, so I was letting you do it this way. So what's that number again? 0.00875 1, 2, 3, 4, 5, 2806. Now we don't need that many digits, but I'm going to hang on to them for a while. Okay? Now, your density, mass density then, is your mass per unit volume. This was your volume. So your mass was 0.220 kilograms, right? Divided by your volume, and that was 0.00. No, I'm sorry, I left off the 0 in front of the 2. Okay, 0.0002806. And that would be cubic meters. All right. Now with your calculator, punch those numbers in. 0.022. You don't have to put that last 0 in the calculator. It doesn't care about significant digits. Divide that by 0.5 zeros, then a 2806. And then hit equal. Whoa. Where?
The answer to that one.
To that one, not you. Okay, I can tell you didn't, because did you put 0.022 as your numerator? 0.022, right? Divide that by 0.000002806, and then press equal. A big number, right?
7, 8, 57.
Okay, tell me again. 7, 8, 5, 7. Okay, blah, 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 right? Okay. We got to round to how many? This had 3 digits. This had 3 digits. So we round to 3 digits. 1, 2, 3, 786, 0. What do they have?
The book, the thing is 7830.
Okay. They must have messed up somewhere. Okay. And that would be kilogram per cubic meter. Okay. Let's see where they did the error. I see where they did it. Okay. They rounded every step. Don't round every step. Use all the digits you can up until the end. Round your final answer. If you get that close, you'll get credit for it. Okay? Those who stayed late last time and we were working on a test question, the way the book did it, they had something being fired into the air at a certain speed, and then they said, how fast is it going when it landed? Yeah, second, yeah. Right, okay? And because of their round-off error, they had it faster coming down than it did going up. Physically, that can't happen, okay? So, round-off errors will cost you, and they rounded off here. We rounded too, but we minimized the rounding until the very end, okay? So I like our answer better than theirs. Okay? Now, ready for the next one? Yes!
No.
Do I need to leave this on a little longer?
Yes.
Okay.
Right now.
Oh! see in the book, they rounded their volume to 2.81 cubic centimeters, and then they rounded their density to 7.83 grams per cubic centimeter. So they had two round-offs there, and they probably built on each other. That's how they got 3 digits off on the last significant digit. But they're awfully close, okay? How are we doing? Again, you could have done it the way they did in the book, done it all in grams per cubic meter, and then done both conversions of grams to kilogram and centimeters to meters, and worked it out. That's what they did. But it's not quite as clear what they're doing. Okay, that was example 2. Let me know when you're ready for 3. Okay? Everybody else? All right, let me erase this. And let's do example 3. Find the weight density. What's the symbol for that? Say again? Weight density? D sub W. Okay? And, find the weight density of a gallon of water weighing 8.34 pounds. Okay? And weight density is, by the way, what? Is weight, which is F sub W over volume. Okay. Now, they want that for a gallon of water. So, 1 gallon of water, and they just say a gallon, okay? And they say it weighs, so it's F sub W, weight, is 8.34 pounds. Okay. Now, what's the problem here, Houston? Pounds are good, but you want cubic feet. They gave you gallons. So again, let's go to the back of the book and see if they have anything here that would be helpful. I don't see it. I hate it when they do this. Okay. I bet you somewhere, and I know what you can do. If you got a telephone, see how many cubic feet are in a gallon of water. But that's not a very good physics answer. Let's see how they do it. Okay, it's the physics toolkit in chapter 1.
It came at 0. It said 0.
What's that?
It's saying that the Google is saying 0.134 cubic foot is 1 U.S. liquid gallon.
Okay, say that again.
0.134
cubic feet is 1 gallon. Is that what it's saying?
Yes.
Okay. I was just going to see, in case you don't have that, but that's what I would do these days. It says other units number 31. Let's see if that's the right page. I don't see that it is. Well, let's not mess with it anymore. Thank you, Google. Okay. So, we got what a volume is. We got the weight is, so we got it. It's 8.34 pounds. They gave you that, and they gave you a gallon, and we just found out from Google that 0.13, I say 13 in the right, 134 cubic feet. punch that in your calculator here. Yuck! If I wrote it down right, that's what you said, right? Huh? Say again? 62.27. Say again?
Not the 7.
Oh, what is it?
7 should be a
3.
3.
62.23. Okay. Okay, that's going to be enough. Okay? Because we only got 3 digits here, 3 digits there. So this is saying that density of water is 62.2 pounds per cubic feet. Okay? Our table told us it was 62.4. So either this is a little bit warmer water or something. Or your gallon isn't exact or something like that. Let's see what we get here. Oh, the book told you that the volume 1 gallon was 231 cubic inches. Yeah, that's helpful. I like Google better. It gave it in cubic feet. And, but they did say this came out to be 62.4. So, again, if you're that close, it's going to be okay. I imagine Google rounded poorly. Okay? Ready for example 4? Can I do it? Yay or nay? Huh? Okay. All right, example 4. Find the weight density. So again, we're looking for D sub W. Well, let's see. Okay. Yeah, I can't get my pen to come back. D sub W, the weight density of a can of oil, 1 quart, weighing, so 1 quart of oil, weighing 1.90 pounds. And the weight, F sub W, is 1.90 pounds. Okay? Now, what's the formula for weight density? F sub W, the weight divided by the volume. And again, we got the same problem. We got the weight fine, 1.90 pounds. That's great. They gave it to us. But they gave us a quart of oil rather than cubic feet in oil. So you can either ask Google again, or we can go by what they give us in the book. Okay, in the book they tell us that they just told us earlier that 1 gallon was 231 cubic inches. 1 gallon is 231 cubic inches. I'm going to put I-N cubed. Okay? Now, 1 quart is exactly how much of a gallon?
Oh, what we just went over.
Yeah.
0.13.
Okay, wait.
0.
No. A quart is what fraction of a gallon?
Oh, 4.
A fourth. So we divide that by 4. 231 cubic inches divided by 4. Okay? And we'll just leave it like that. Okay? So that's going to be cubic inches. Now, the question is, do we want to get that to cubic feet now, or do we want to wait until after we've done our math? And I really don't care. Either way, got the same thing to do, either one of them. You tell me. You want to do the division? Okay, you want to do it like they have it in the book? So they do it.
They did the division and then they did the conversion of the units.
Okay, so they do the division first. So now, here again, I'm suggesting that you keep the units. I'm telling you right now, they're rounding. When they say 57.8, they're already rounding. Okay? I say don't round yet. Okay? So what we're going to do is take this and divide it by 231. In fact, let's go on and do our division.
It's 59.25.
Second? Wait. Okay. Yeah. And what do you say it was? 57.75 cubic inches. Okay. Good deal. You notice what they did in the book? They rounded to 57.8. Don't ever round in the middle of a problem. Wait till the very end to round. Okay? They're introducing an error there. Okay? So we're going to do 57.75 cubic inches. I can't write. Okay? So do that math. Calculator time. 0.0329. Okay. Leave that on your calculator. I'm going to just stop there writing. And this will be pounds per cubic inch. Right? Where you got to get pounds per cubic feet, that's what they usually measure weight density in, right? So we want pounds per cubic foot. Okay? Now, what unit do we need to change? The inches to feet. So what unit goes where? Inches on top, feet on the bottom, and then match the numbers with the units. What would that give you? 12 inches, 1 foot. Perfect. But we need cubics. So cube, 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 and cube. Okay? You have to cube the units and the numbers. And so here's how you're going to do the math. Whatever you have on your calculator, you still got that 0.0329, blah, 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 blah. Leave all that on there. Multiply it by 12, by 12, and by 12. That's 12 cubed. Notice your cubic inches go out, and you're dividing by 1, so that doesn't change it. Say again? Okay, a little bit louder. I mean, slower. 56? Okay. 56, is that right? 0.85. Okay. And then they would round that to 56.9 pounds per cubic foot. Now that's what you got to, or is that what they got?
I got that on the calculator.
You did? Okay. Okay. Well then, their round off didn't hurt them because they rounded one way one time, the other way the next time. But generally, don't round too early. Okay? All right, good deal. That was example 4. Okay? I'm afraid we're not going to have time for example 5, are we? Boy, she didn't even look at her watch. Okay? Oh, does it? What does that say?
5, 4.
You sure we can't do it in 4 minutes?
It's too much conversion and figure this out.
Okay. So we're going to begin next time with example 5, right? Now, if you'll notice, there's just a couple more examples and we're through with the chapter. Okay? Now, let me give you a few homework exercises. I didn't do that for the last section, did I? Well, they didn't have any, did they? I don't think they did. Okay, so homework exercises. Do sum of the odds, 1 through I would say probably 23. Okay, let's see. Maybe not that far. let's just do, well, do as many of them as you want to. Don't get into specific gravity. We haven't gotten there yet. Okay. Now, here's the question for you. I think I've got your test run off. You can have the extra weekend to work on it. It's not going to start your due date any sooner. When we finish the chapter next time, then it'll be due a week from then. But you can have all the time you need. You want it now? Okay. So let me get it to you. No, I asked for them to run it off. I think this is it. Nope. That's the previous one. Ah, here it is. Okay. Now, don't go until I explain something. Goodness, I'm stiff. They make so many errors in this testing. And I found 2. I hope there's no more. But if you run into problems and things don't look like they're making sense, ask me, and I maybe, and you can just tell by looking at this one. Look at number 3. The vertical steel columns of an office building each support a weight of 50,00 pounds. What is that anyway? There's no such number. You need 3 zeros after a comma. And that's what you put. It's 50,000 pounds, with each being compressed 0.0260 inches. What is the spring constant of the steel? That's the A part. The B part, what would be the compression? What would the compression be if the weight were 60,00? Again, that makes no sense. It's 60,000 pounds, 60,000 pounds. So the both of those strange numbers there should be the first 50,000, the second 60,000. Okay? And I thought that the last time I did this, I found another one somewhere, but when I looked through it, I couldn't find it. So that's why I say if you run into something that looks like an error, let me know. And I'll try to check it out. Yeah, the question part of 3 was 50,000, and the B part of the question is 60,000. And the 60,000 at in part B. All right, and that probably took us very close to 4 o'clock, didn't it? I mean, 6 o'clock, right?
Right at 6 o'clock.
See, I didn't cheat you out of any of your tuition dollars, did I? Okay. I was afraid I might. Okay. Good deal. Have a good weekend. Second.
What was the formula to 10? Or you
What's that?
listen to that thing on the test, on the last test?
Okay. And what was it? What's the question? Okay. Yeah. Yeah.
So I got the same question she had.
Okay.
Tuesday I wasn't here, and I know you said after class you. I guess I'm trying to figure out what formula.
Okay.
I think I wrote down one formula.
Yeah.
At first I tried to solve for the potential. The EP is M times G times H. But I wasn't sure if I was doing that one right.
Okay. What did you say?
On number 10.
I know, but what did you say you tried to solve for? I couldn't
The
understand.
potential.
Energy?
Uh-huh.
That's certainly one way to go, except, okay. Are you asking about the A part?
Yes.
Okay. I'll leave this on so others can listen too. Here, you can have yours. Let me find mine. This is the one that starts with find the work done, right? Okay. All right. Now, you fire a bullet into the air.
Mm-hmm.
Okay, it leaves your muzzle at a very fast speed, 123 meters per second. Okay, it's going up. So what's it doing as it goes up?
Moving.
It's moving for sure at the same speed.
Oh, it's going faster. It's going up, ain't it? No.
Really?
It's going slower.
Yes, it starts slowing down because gravity is pulling it downward.
It's going
So after 1 second, it's going to be 9.80 meters per second slower. No, wait, don't
I'm just
get
right.
carried
1
away.
second, 9.8.
That's the acceleration due to gravity, meaning it slow it down that much. The next second, it's going to slow it down again.
Yeah.
Next second, it's going to slow it down. It's going to keep slowing down every second until at the highest point, what's its velocity?
It's gonna be the lowest.
Second, that's going to be the lowest kinetic energy. What will that be? What will its velocity be at its highest point? What will it be? Velocity.
Is it a 0?
Yes, it is. Because if it was any faster, it'd keep going up.
Yeah.
So at the highest point, it's got to be 0. That's all you do through the first one. Is think
I
through
don't
it.
know. I guess I overthought. I was thinking a little bit too much on that one.
Okay?
And then the next one, like the maximum height it reaches is when we did, is when like the other problem we did on the board when they had like the 1 second, when you was trying to find the potential and kinetic.
Okay.
And
Actually, we came up with a formula based on those two that gave you, that related exactly what they told you here. The speed, initial velocity, and height. What was the formula that related just those two things together?
you said the speed and the height.
Height. It was one formula that related those two together.
Speed is the
Yeah, I knew you're the formula queen. That you got to have those somewhere.
speed is distance over time.
Okay, yeah, but this is later. Speed and height, when you're talking about energies, potential and kinetic energies. The speed,
Okay, we looking for the GPEs.
what's that?
Some of the GPEs.
Yeah, when you're dealing with that. We came up with a formula. I know I can show it to you in the book pretty quickly, but
You said a formula for the what? Kinetic.
it has to do with velocities and height. Has those two things in the formula. May have something else too. Huh?
1 mass times velocity squared.
Okay, that's the kinetic energy. A little bit further down.
GPE at the top was the GPE.
Second.
Reading for the bottom. GPE at the bottom. Is
Okay, we got that, but a little bit further down. Something that related only velocity with height. Yeah. Okay. If you're relying on the book, I can show you that fairly quickly.
volume equals square.
Hey, what's that?
The square.
Of what?
Square root. The square too.
Square root of
That's the volume. The square G.
the velocity.
Velocity of the G.
V is equal to the square root of what?
G times H.
2GH, isn't it?
GH.
You see that? Okay.
I got it right here.
Oh, that's
Okay.
On the cover, it's 8.4 conservation and mechanical is what it's upon.
Yeah.
The
Velocity equal.
the height over
No, okay.
Gravity times height.
Okay.
It's 2GH.
Yeah, 2GH under the square root symbol, right?
Yes.
All right, there you have it. Okay, I'll write it down. V is equal to the square root of 2GH. Now I know what 2 is. What is G?
9.80.
Oh yeah, that's what it is. Okay. So we have V, and they gave you V, didn't they?
Yeah.
Okay. Second.
123 meters.
123 meters per second is equal to the square root of 2 times
2GH.
And what is G?
9.80.
9.80 meters per second squared times H. And they're asking for the height. What's the maximum height reached? If you do the math, you should get that H.
Okay.
And how do you do it?
So you're going to first do the square root of 2 times 9.
Okay. You can't take the square root of something you don't know. You're
We
trying
gotta
to
do
solve
2
for
times
H.
Oh, yeah.
9.
No, you got to divide the 123 to get,
Not divide.
or multiply, because you're trying to get the H. Right now we don't
Trying to
have
get the H.
So we have the G. and we
Okay,
have the B.
wait. You can't do that yet. What you got to get rid of first? What's in the way there? To isolate the H.
You got to get rid of this part.
No, not yet. There's something else in the way first.
Or the second.
The square root.
The square root. How do you undo a square root?
It put the decimal.
How do you undo a square root? Oh, sure you do. Okay, if you think back where this came from, you had a 1/2 mv squared is equal to mgh. Remember? That's where that came from. Remember?
Yeah.
1/2 mv squared is equal to mgh. That's where you came from. Kinetic energy at the bottom is equal to potential energy at the top. Remember? Okay? And the first thing you did, or one of the things you did, was get rid of the m's. That's why you don't have a mass in there anymore. And then you multiplied by 2 to get rid of the 1/2. That's where your 2gh came from. Then you went from this to that by, oh yeah, so to go backwards you square. So what that means is how you undo a square root is square. So this is v squared is equal to 2gh, and go from there. Right? Now you divide by 2, divide by g. Oh wait, yeah. Yeah. You square your v, 123, square it, divide by 2, divide by 9.80, that gives you your height.
Okay, 123 squared, then we divide by 2.
Yep.
Then
Divide again by 9.80. And that gives you your h. Pretty far up there.
turn calculator.
What
Now,
you
how many
get?
numbers we supposed to keep after we squared?
Okay, how many were you given? 55.0, that's 3. 123, that's 3.
So 11.0. Or we gonna round the number up?
Okay, where did you get 11.0?
The square, did you say 123 square?
123 squared, let me see you do that. Is that squared or square root?
Oh, I'm doing square root.
Yeah, you got to do square. When you square a big number, it's going to get even bigger, much bigger. Yeah.
29652
Okay.
So you able to put it in your thing like that?
Okay.
Yeah, that's just square root. I mean, square right there.
Okay.
So like if you
Right
did,
here.
if you cleared it out and do the 123, and then do square. See, that's square in the 123 just by itself. Then you gotta multiply the 2 times 9 times 8.0.
Then you gotta divide, right?
Yeah.
Yeah.
Divide by 2, which is now 7, 5, 6, 4, 5. Then then
It's
you
like
divide
when I'm
again,
at
but
home,
we
this is so confusing.
you
trying to
divide
figure
it
it out.
again by the 9.80.
Say that again.
We divide it again after we
Okay.
by the 9.80.
Okay. You have to explain the steps you've done so far.
I done already squared, and after the square,
Right.
I divided by 2.
Divide by 2,
Uh-huh.
and then divide by 9.80. You got to divide by each of them. Because you're trying to isolate the H.
And then I got 77,188, and you said we doing
3 digits.
Yep.
So it would, we round, so it'd be 77.2.
772, that's right.
So it's gonna be 3 answers for number 10.
Yeah.
Yeah.
ABC.
The first one was
0.
what? 0. The second one was
772.
meters per second, right? No, meters. Maximum height.
So like when I'm doing these at home, like the first one, the way the books, I tried to go back and do it like according to the examples in the book. So those
Right.
part I could get, but as you get down to like number 10,
Right.
I'm like, now I have this formula, but I know I gotta solve for this. So which way do I go?
Right.
That's the part that gets confused.
Mm-hmm.
This is my
So like I
baby
said,
doctor's office. I'm gonna turn this
what-
in. You can
the
grade it. I'm
velocity
gonna come back real quick. Hello.
does it
Okay.
hit the ground? So let's see.
Okay, can I shut down the recording?